All right, let's learn about Newton's laws of, wait for it, rotational, oops, rotational motion. Uh, what you'll find here, and I said this in a previous video, almost everything that works in linear terms is the same in rotational terms. You just have to kind of think of a spinning reference frame instead of a linear one. So we're going to go through Newton's laws and we're going to rewrite them for rotational motion, but you'll see that for the most part, it's exactly the same. Rule number one says in linear terms, an object in motion will stay in motion, an object at rest will stay at rest unless acted on by an outside force. Well, if we want to just change it to the rotational version, we can say an object in angular motion, angular motion will stay in angular motion. An object at rest will stay at rest until acted on by an outside, get rid of force, and I'll write in here torque. The minute that we have a torque acting on it, it can cause it to start spinning or slow it spinning down. But really, we're still at the exact same idea as we were before, that an object stays at rest or maintains the same kind of motion that it's always had unless something from outside the system acts on it. What this means is if I was in space and I took a top and I started it spinning, it will continue spinning forever unless something outside slows it down. On Earth, we don't see that because there's friction and air resistance and all kinds of other things that can happen that end up slowing it down. So if you do a top on the Earth, you're very familiar with the idea that it will stop. But that's not true in universal terms. The only reason it stops is because there's those outside torques acting on it. So same rule that applied to linear motion is applying in rotational terms. Our next one, the acceleration of an object will increase with an increasing net force and decrease as mass decreases. We can rewrite in angular terms. We'll just call this, in fact, hold on. There we go. The fish acceleration of an object will increase with an increasing net torque and decrease as, and this is going to be a new idea, as the rotational inertia increases. We already talked about mass as the idea of inertia, resistances to changes in motion. Now we have rotational inertia as the idea of resistances to changes in spin. So a large rotational inertia resists the change more heavily, which means it's harder to get it to start moving, to get it to speed up and slow down and such things. So I can rewrite this entire equation into rotational terms and say fish acceleration is equal to the sum of the torques, or outside torques, over, and our variable for rotational inertia is I. So you can see that it follows a very familiar format, and solving these problems will feel very similar, with the exception that we're going to kind of draw those torque diagrams that you saw in the last video instead of free body diagrams. Number three is probably the biggest place where we're going to have to take a step away and recognize some of the differences between linear and rotational motion. In linear terms, we say every force acting on an object, or for every force acting on an object, it exerts, it being the object, an equal and opposite force back on whatever caused that force. But in rotational terms, that doesn't really make sense if we just swap all the words for torque. If we did swap all the torques, we'd say for every torque, there's an equal and opposite torque on the other object, but that wouldn't make sense because if we had two different sized circles, they would apply the same force at the outside edge. But because one of them is bigger than the other one, it would have more torque acting on it than the smaller one would. This is actually important when we're talking about gear ratios and mechanical advantage, but it kind of just throws out the idea that we can just plug in the word torque here. Instead, we just won't change Newton's third law. We'll say for every force acting on an object, it exerts an equal and opposite force on whatever causes that force. And then if we're trying to use it in rotational motion, we'll just figure out what that means for the torques after the fact. So we'll know that F1 equals F2, and then we'll just figure out what that means in terms of torques. So this is the only one that we can't quite just do a word-for-word replacement. We could say instead that, how did I write this now? A torque is caused by, a force, and then we just say for every force acting on the object, it exerts an equal an opposite force on whatever caused that force, leading to different torques. So that one kind of gets more wordy and less useful, but just realize that the forces stay the same. That's still true, but the torques that come off of that is based off of the radii, which can lead to different torques on the different objects. So that's the quick version of the Newton's laws of rotational motion. Hope you feel comfortable with the idea that much of what you already know is just being reinforced in this unit. And in fact, you should find that you get better at linear motion by practicing this rotational motion stuff. All right, thanks for watching.